And welcome everyone to our discussion on supply chain management. Ashwin Pingali from DZ Solutions is joining me. Ashwin, great to talk to you today. Looking forward to discussing much of the nuances of using graph technology or taking this connections first approach to supply chain.
Thanks, Jeff. Thanks for the opportunity, and thanks for allowing me to give this talk.
Yeah, my pleasure. So very quickly, folks, we're going to end up. This will be a fair, a quick and I think still very informative agenda and discussion. We'll talk a little bit about the Neo4j background. We'll talk about the age of connected data that we feel like we're operating within. And then we'll discuss some of the core sets of issues and the complexities of connectedness in the supply chain. And then Ashwin will discuss much of his perspective on how to deal with that. So as we look at where Neo4j is sitting in the marketplace right now, we talk a lot about graph technology. We talk a lot about looking at the world through a lens of connectedness. We've been doing this for over 15 years now, and we are indeed the largest dedicated investment in graph technologies. And as you can see, we've developed the largest community of graph operators and participants, which includes partners like Ashwin and startups, as well as commercial enterprises, and the gargantuan community of developers and those associated with using Neo4j, either in its open source or its commercial forms. When you look at historically where we've been investing and how graph technology itself has evolved, if we look at this from simply the technological kind of perspective, when we first defined the property graph and released Neo4j as an embedded open source, then we started to see decent uptake, but we kept realizing that making information and access to graphs easier and easier was a key goal of the project, which led to the development of Cypher, the declarative query language. It led to the authoring of the O'Reilly Graph Database book. We introduced and continued to evolve the labeled property graph model, introducing labels to the property graph in 2013. We're trying. We introduced the Neo4j browser, again, helping visualize and blend that activity between having a graph idea or a connections first kind of concept. When you conceive the idea, you want to make sure that you're preserving relationships. And then when you start to code that activity, you want to make sure that those relationships are preserved. And then when you compute and deploy those activities as an application solution, you want to make sure you're persisting those connections. Relationships are indeed precious in our regard. So you'll see when we talk a lot about that native versus non-native graph technology, or different applications of why the connected first kind of approach that we're taking, and why this Neo4j, the way we're discussing what we're doing, is to drive home that concept of connectedness, as you think about it and draw it on a whiteboard, as you code it in Cypher, or as you compute it within your application. More recently, the Open Cypher project has been very busy. A couple of things of note that they've released recently is Cypher for Apache Spark. That puts the Cypher toolkit on top of the Apache Spark engine, so that you can materialize graphs out of your big data investments. And very recently, Cypher for Gremlin. This is a brand new open source release that is intended to help Gremlin users and Apache Tinkerpop users enjoy the simplicity and kind of that ASCII art elegance that Cypher offers. And finally, you'll see throughout the course of 2016, 2017, and 2018, we continue to build out the the Neo4j platform, both in community as well as enterprise, and coming soon as well as cloud kinds of pursuits. So keep following us for those kind of progressions. Now, we really love to talk about different customer implementations. Many of them are very noteworthy and newsworthy, as you might have seen. But what I want to do is try to tie these into the supply chain sets of activities. So fraud detection and making sure that you understand what's happening within the financial transactions of your supply chain when perhaps a buyer or a supplier is doing business with you. The ICIJ's activities of Panama Papers was a reveal of how to trace money flows and how to trace where different accounts are being held and who's holding them. The NASA knowledge graph is actually a parts assembly and historic, delivery chain to areas out in the stratosphere. Right. You can imagine that one of the biggest jobs on the planet is to try and figure out how to deliver cargo and eventually humans to other planets. So that in itself, as a supply line kind of problem or perspective, is exactly what the NASA knowledge graph is trying to help with and make sure that all the lessons that NASA has learned historically are either applied or expanded upon in their newer research as they go and develop their system of delivery to put people on Mars. And to date, they recognize that this lessons learned database has probably saved them well over $1 million in years worth of research or reinvestigation kind of activities. And the eBay knowledge graph called eBay ShopBot is an example of making that customer experience really very, very modern in the delivery of conversational commerce kinds of applications. So this is the front-end customer-facing perspective in an omni-channel world of that overall supply chain experiences. How are you able to get goods and services from supplier, producer, distributor, all the way through into the customer's hands in an efficient and cost-effective way, while delivering that digital kind of perspective for that. Some other additional ones that will be feel very close to home is these real-time promotion applications, as well as Marriott's pricing application, are really goods and service delivery vehicles where we are making the real-time recommendations for websites who are pricing out and making shopping cart recommendations to buyers. This particular retailer enjoyed significant record-breaking kinds of revenues on Cyber Monday because their website didn't crash, their shopping cart didn't crash because it was queued up with too much stuff. Marriott's example is delivery of real-time pricing information about hotel rooms across their 5,000 properties, and taking that activity and not only making it more efficient, but also making it perform at proportions of scale that they had never really thought of before. That 10x transaction throughput is one of the paths that they were following, but they're moving 300 million pricing operations on a room-by-room basis through this system, and they're doing so on roughly half the hardware that they were using originally. So imagine the overall value proposition of this: 10 times more transactional throughput with orders of magnitude more transactions, yet a reduction in the back-end infrastructure costs. That's the kind of efficiencies that we're trying to drive. And then the package routing in real time. We have a very large European delivery service that's using Neo4j and dealing with 5,000 plus routing operations per second in terms of making sure that packages are going to the proper destinations in the shortest paths, regardless of what their sort of peak optimizations are. So let's look at kind of the core, forces that we're seeing in the in this data-driven world, and oftentimes we're going to end up characterizing throughout the course of this year all of these activities from the lens of being a digitally transformative kind of operation. Most of the data that is generated has been in the world right now has been developed over the last 2 or 3 years. It doubles in size every 3 years, and we're dealing in how to optimize and how to make a customer experience that blends people like customers, the processes like delivery of goods and services through the supply chain, assets like those products themselves across networks, and using new age devices to make sure that this all happens efficiently in a cost-effective manner. So that's really this, the forces in the data-driven world, but certainly in the driving the complexities of supply chain delivery is where we're seeing a lot of demand. And really, when we break this down, we're looking at how the connected nature of the networks of people that we're trying to deal with. As I said, it's either customers, it could be suppliers, it could be partners, it could be raw material suppliers. The business processes of how you actually move these things from one location to the next, or optimize the delivery of a service in terms of timing to make sure that, let's say, payments or mitigating risk are indeed happening within real time and at the point of pain, where in support of these kind of business processes, we're blending the people activity with these business process and systems activities, and then also operating upon those digital systems and networks that all of this is happening in, whether that's location based, whether that's operationally based, whether it's incorporating RFID tagging, devices, other IoT kinds of capabilities. All of this is playing itself out in this rise of connections in data. This data connectivity and the relationships among them are really a lot of the core drivers of this digital transformation kind of activity. So we're seeing this in manufacturing of and delivery of drugs, in delivery of food, in delivery of healthcare services, in delivery of oversight of security, oversight of risk management, and then in terms of delivering that great customer experience to those who are the ultimately the end shoppers or the end buyers or consumers of the services that we're delivering, powered by AI and machine learning in many cases. So this is kind of the potential of what we're seeing in the supply chain space. Of course, we're trying to bring to bear the community of users and the community of partners to apply themselves to these sets of areas of problems. And when I talk about the areas of problems that we're going to discuss in a second, the areas that I'm really thinking about are the complexities that we find in core sets of supply chains, whether they are the customer experience part of the supply chain on the upper left-hand side, what's understanding and forecasting demand, what my new customer orders might be against my backlog, whether I'm actually shipping them, are they satisfied, and then how is the origin of products in that chain playing out. Those are all areas of efficiency that we can gain. There's the digital information in the center here of working through the chain, whether it's product inventories, whether it's core attributes of products, locations that they're supposed to be going, optimal routing that they're supposed to be taking on, and then when they are indeed delivered to consumer or delivered to distributor, even what are the costs associated with that? What are the billing systems associated with that? And then how is information flowing across all of these areas? My final summary of this and observation, of course, is I'm certainly not the expert here as Ashwin is, but the observation is this is incredibly complex sets of networks that we're dealing with, and incredibly complex sets of problems that intersect with each other as part of this overall supply chain delivery set of activities, whether it's making sure that raw materials are getting to manufacturing plants, whether it's the making sure that warehouses are properly stocked and we have a core understanding of timelines when inventories are going to be available for field warehouses or distribution centers or retailers, online delivery, shippers, last mile kind of sets of issues, all the way to end customer. Right, the complexities here are unreal, and that's one of the great opportunities we have to bring graphs into the mix. So as we research much of the sets of issues that are going on in supply chain today, there's really what appears to be four kind of overall areas. First one is that customer experience and service demands upon the network, upon the chain, to make sure that goods delivery is speedy, high quality, has attributes of things like free shipping, has transparency so you can track where anything is at any given time, and of course do so across omni-channel kinds of delivery vehicles. Check from my phone, check from my computer, check by a telephone, and and stand at my doorstep and wait for my goods to arrive. Match this to situations in the industry like a labor shortage of drivers, an introduction of the sharing economy. So whereas Uber and other ride shares are now taking on package delivery, taking on additional last mile efficiencies, like let's try out drones to see if we can land on a doorstep with a small piece of goods. Right, those are all customer experience related type issues that are that the supply chain organizations and supply chain delivery vehicles are facing right now. They're looking at a lot of technological hype. Whether it's IoT, whether it's robotics, blockchain, 3D printing is supposed to save the day, but the activities around remaining flexible are really still of top concern, as is cybersecurity, right? Every transaction needs to be secure. Every transaction and piece of customer data that you're holding needs to be protected. You have additional in the globalization section. You have regulations that you have to adhere to when you're handling those sets of the financial transactions or the customer data, and those vary oftentimes by country. In the U.S., state by state, federal regulations, local regulations, tariffs. All of these are adding to those sets of complexities. And then, how do we make sure from a number three here, we're maintaining transparency and visibility in this orchestration across this very complex network? So you want to avoid situations where inventory is spread too thin. We see customers who are able to identify and recognize when cold weather goods need to be shipped north, right? And warm weather goods should be moved to the south until springtime. We need better visibility into overall inventory management. We need better coordination between warehouses, stores, distributors, salespeople, and we need traceability. Right? We have customers right now who are offering capabilities in product origin traceability for agriculture and food products. But this also holds true in the pharmaceutical supply chain or the drug delivery supply chain, is making sure that we're able to support that kind of visibility so that customers, again, will trust the process, right? That's one of the keys. I want to talk very quickly about Neo4j as a connected data platform and a vehicle that you can use to begin to integrate not only these processes, these people, and these digital systems, but take a how to look at the world from a connected data kind of perspective. Starts with the core foundation of Neo4j database. It's great at building applications that are real time, that give you that kind of transactional transparency and visibility. And it also supports graph analytics, so you can figure out as you add perhaps distribution centers, what might be shortest path to customers in that local area now that a distribution center is nearby. That's what graph analytics can help offer, serving data scientists, serving data analysts there. And then coming up with ways to best communicate your particular objectives using visualization tools. So discovery visualization for business users, one of the core sets of drivers of this overall platform. More recently, in terms of a feature-by-feature approach, things that we have rolled out or and announced in late 2017 and early 2018. Things like supporting a better developer experience, supporting data integration across a variety of different systems, because in order to address the complexities of what supply chain happens to hold, is we're trying to make sure that we can indeed map, trace, and connect all these different data sourcing vehicles that you are very likely to encounter, whether that's traditional relational systems, big data systems, data lakes across a variety of different types of organizations, etc. The database itself continues to both become faster, support significantly larger scaling operations, and do so in a dependable, reliable way. We look at the world from a lens of data integrity, and the preserving the connectedness of data overall is goal number one for Neo4j, and then all problems are borne out after that. But if you're not making sure that the data is indeed true, that the connections are intentional, and they are not broken or lost, that's a very big focus of the database itself. Analytics we covered, the graph algorithms for supporting what are the most centrally located kinds of activities. What are the dense nodes, right? A distribution center might be a very dense node for delivery of products. What are the short pathfinding algorithms we can apply? All of these can be used across the board in that complex supply chain network. So roles in the and types of projects that we see as bearing themselves out in this space are really this idea of connecting the roles and expectations of participants with the delivery processes and the overall digital systems upon which we're delivering them. We see that as being giving us access and visibility into a wide variety of user types as well as project types, which is really what this slide is depicting, and applying all of this upon a using both a connectedness lens as well as a supply chain management kind of lens. And finally, the real basic advantages of why would I use graph, and as opposed to my existing systems. If you look at the world of existing systems, right, they're really good at storage and retrieval of data, but they're not necessarily really good at revealing or developing connections in data. And of course, Neo4j reveals connections in data, and that allows you to take advantage of more opportunities to do things with that data. When data is operating within Neo4j, it becomes more valuable the more connected it becomes. The more connected it is, and the more densely connected the data becomes. So you put some data in or new data in, and when it's connected to existing graphs, it becomes even more valuable. And that's really an example of the continuation of Metcalfe's law of the network. Right, nodes on the network, the value of the overall network grows with the number, the square of the number of nodes. We believe that happens in data as well. Finally, the core architecture things of why do I care about Neo4j? Can't I do this in traditional NoSQL systems? Can I do this in regular SQL systems? And the answer is sure, if it's one or two hops. But if it's more than 3, you're going to want to look to something like a native graph architecture, born out of within Neo4j, because of our ability to give you a very, very predictable cost of what it takes to hop from one node to the next. And a node could represent a product, in its supply chain pathing. A node could be a customer, a node could be a financial transaction. And when you have to map all of these things together, it's very likely that you're blending 5, 10, 100, 1,000 different traversals within your system. You want that to be as dependable and as predictable as possible. And that's what this feature called index-free adjacency offers us, is as the system scales and grows and increases in value, the cost of actually executing a query or a transaction is very, very predictable and linear in its in how complex and how many hops it's actually making. Basic benefits of the platform: it does real-time processing really well. It's intended for very high performance. Oftentimes we characterize this as minutes to milliseconds kinds of speed. It gives you agility to make adjustments in the overall graph system. And that's a great attribute of the property graph model. We offer visualizations. Developer productivity remains really, really high. Folks love using Cypher itself. We have customers today who, when surveyed, recognize Cypher as being at least as easy to use as SQL, if not significantly easier to use than SQL. In fact, a survey we did in late 2016, 90% of Cypher users said it was at least as easy to do as SQL, if not easier. And we do this in an environment where hardware efficiency, where processing efficiency are always in play, and always trying to make sure that things are as optimized as possible. So common patterns that we see, and this is as you think about weaving that network, that supply chain network together. We see moving tabular data and exposing connections through relational database conversions. We see silo integration as being a very common situation of combining data elements from a variety of different sources or data store types, and then finally revealing patterns from data that's dumped in a data lake, but may indeed not be driving the value that was originally intended. Well, relationships tend to drive that value. And I think as I wind down here and set up for Ashwin, the core sets of differences that Neo4j, our connections first approach, is really to make sure that connections are persisted from the time that you might think about it and visualize it, from the time you conceive the idea of connectedness, to the way that you write connectedness in a query language, to the way that you compute it, whether through both processing and storage. Your data and your application is always taking this connections first approach. We're not breaking connections. We're not transposing connections. We're not relying on other technologies to maintain that connectedness that it wasn't really intended for. And so we see with non-native solutions, you might visualize it, but then you have to transpose it at query time. You have to transpose it again at processing time. You have to transpose it again at storage time. So you lose a lot of that that value and that efficacy of the relationship and how important it is when you're transposing your information from layer to layer to layer to layer, right? You lose hops, and in many cases, you lose consistency, you lose data integrity, you lose relationships themselves. So that is areas where areas of focus that we think the native approach is really, really important here. So I went through the customers there, but now let's talk about a real world situation with Ashwin Pingali. Sorry, I think I put too many N's in there. But Ashwin, do you want me to stop screen share and bring you up, or do you want me to drive your slides?
No, I can take the slides over. I'll take it over.
Very good. Then there's stop sharing and
can I share? Okay.
Here we go.
Yes. Yeah, I own actually two companies. One is DZ Solutions, which is a product company, and I also have a consulting firm where we are dealing with the supply chain and enterprise-related solutions. So in this thing, we are looking at a specific set of solutions that we have built on top of Neo4j, and I'll go in deep dive for this. The target audience for this, we'll just go over who we are actually looking at, what are the opportunities that supply chain presents, what are the critical planning assumptions we make and we really ignore, and how Neo4j presents a value proposition and what is the solution going to look like. So the target audience here we are looking at is basically customers who have invested hundreds of thousands of dollars in planning systems, the ERP, SAP, and the associated planning systems that integrate with these ERP systems. And they're also still dealing with the inventory level problem, because even though they have invested in these systems, the problems of inventory level optimization has not been achieved by most companies. And the reason for that is something that we'll touch upon a little later. But the big question for any supply chain professional is three questions. Okay, what is it that I'm going to buy? And when should I buy it? And how much should I buy it? The what to buy is a connection with the products that are actually being sold by the company. The when is a time connection, right? When should I buy this? When should I buy this next week or the week after? And so that I don't have too much on my warehouse shop floor that I have to sit on. And all of this is automated these days. But this automation is only going to be effective if some of these assumptions that are being fed to these automated planning systems are in line with reality. And these assumptions are never updated. So they definitely are never in line with reality, because once the system is in place, people never update things like lead time assumptions. Lead time assumptions at a supplier level or an item level constantly fluctuates, and it's very rare. And we did some surveys and we found that most companies never updated their lead time assumptions at a supplier level or an item level for all of their items, or at least for their A-class items. The min-max assumptions, this is probably one of the most used supply chain technique, where there's a min-max algorithm that runs, and that algorithm requires the minimum and maximum safety stock, and minimum and maximum stock levels for every item. And this assumption, I have rarely seen this being updated in a system. And the third is something called reorder point planning. And the reorder point planning is requiring an assumption called the days of stock, how many days of stock that I need. And underlying all of this is what to buy. What is my demand going to be for a particular product? That is still a very big question, and companies have invested in products like Dimantra and others that do some level of sophisticated forecasting, but many of these systems do not take into account the connected nature of the transactions. They don't take customer-specific demand patterns and buying behaviors, unless, I have never seen in many of my clients, they have never done look back at their customers and how they purchase and when they purchase, especially in the B2B scenario, which is very, very important to figure out what the demand is going to be for different kinds of products. So so let us look at the first assumption that we look at, and this is actually a screen from the Oracle ERP screen, where you see a min-max quantity and an order quantity. So these four parameters need to be updated for every item. So imagine that an organization has 100,000 items, and they also have 15 warehouses or 15 plants, whatever they are, 15 inventory orgs. And if they have to do this update, they have to update around 1.5 million records. And they have to do that on a frequent basis, right? And nobody does that. Okay, nobody has invested or done anything to update these assumptions that would be actually critical in reducing the inventory levels. And we'll show you how, for a simulation run, how much the inventory savings would be even for a single product. The reorder point planning, again, you're seeing a similar screen for an item that has a planning method of reorder point planning method. And there you are seeing the number of days of inventory that you need, or the percentage of inventory that you need. And this is something, again, these are non-MRP planned. I'm not even talking about the advanced supply chain planning. And advanced supply chain planning takes into a lot of assumptions, especially the purchasing lead time and the different suppliers that are out there and who to buy, etc. So all these assumptions that go into these planning engines are never updated, or if they're updated only with the some active domain specialist who's actually doing that, but it's never done in an automated fashion from an IT perspective. So what we are talking about here is having a method to do this min-max planning in a dynamic fashion. So here I'm just presenting you a small case study, and I can actually run these things. So we ran this for a small product, okay? And we looked at the product and we looked at the average inventory, and it had a static min-max of around 440 was the average inventory. And we looked at how those levels were. So the first thing that we did was we tried to identify products that had a very high average stock on hand on a monthly basis. And to do this, Neo4j is extremely useful because Neo4j can actually store the connection with time, and the connection with time gives us the state of inventory at a particular day. And how that state came into being is also something that we can get from the connection. It's based on a purchase order, or it's based on a return. So you can actually see how the inventory came into being. And we also can see the purchase order that was actually received, when that purchase order was actually placed. And so we can actually even see that lead time, and we see the fluctuating lead time as well. So the first step we did was we looked at the average stock of that particular product, and we identified products that had a high average stock or a high on-hand inventory compared to the sales. And once we identified these products, then we took one single product and we did a dynamic min-max algorithm. So what this does is it will actually automatically change the min-max values, and it tests out several values. And it also uses a deep learning algorithm to predict what the demand is likely to be. And it uses a deep learning algorithm, a DPAR forecasting algorithm that takes into account some graph features. And the graph features that we do here is basically identify customer-specific buying behavior. So we group these customers who have similar buying behavior for that product and look at their past buying behaviors to figure out what the demand is likely to be in the next demand period. And then based on that, we evaluate different min-max levels, and then we create the min-max levels. And we did this on a monthly basis. So we just did this on a monthly level. And we found that if we had run this algorithm, actually we could save the average inventory percentage reduction of almost 39%. And we could save up to 28% in inventory handling carrying costs. And we, of course, made some assumptions here. And the inventory carrying cost assumption here is around 25%. Usually, the carrying cost of inventory varies from industry to industry. In certain industries, it's very high, especially if there is inventory that's going to become obsolete or it's going to be spoiled, like in the food industry. And it's also very high in the pharma because drugs expire. So we are actually looking at a few companies where we are actually talking to, where we are trying to help them with understanding what their demand patterns are likely to be, and automatically setting their min-max levels to estimate what these min-max levels are. And this is all done through a simple API. So what we do for this particular solution is we hook into the ERP system. In this case, we already have built some extractions for Oracle ERP. We extract the transactional data, and when we are talking about transactional data, we are really talking about all of the purchase histories and also the sales order histories and the inventory transactions, the movement between different inventory sub-inventories. And once we get that information, we use that to understand what are the new planning assumptions going to be. So the first thing is the purchase lead time is usually not correct, because just as the demand is stochastic for the organization, the supplier also faces a similar stochastic demand. So they cannot always fulfill their supplies or purchase orders in time. So their purchase order lead time varies, and this variation between the purchase order from the supplier and the demand variance together, and the lack of not changing your the planning assumptions like min-max and the lead time is actually contributing to a lot of money left on the table. And just by changing these three things, we found that we could actually save companies a lot of money, and that's what this solution is for. And so we have a simple implementation strategy for this. It takes a team size of around 3 to 4 people. We do a pilot project for 12 weeks. In this pilot project, we do a 2-week data extraction analysis to find which items have the most on-hand inventory and which items have the most volatility, etc. And then we spend 4 weeks in designing the graph, the connected graph. In this case, we are not looking at everything. We are just looking at the purchase and the demand of the product over time. And we try to get as much as possible, as much history as possible. And once we take that, we build an ERP API that actually takes this information and figures out what the min-max levels are or what the reorder point levels are. And then we do a pilot support for 4 weeks after the solution is in line. And we can actually take this pilot to a production level where we do it for all the Class A items to actually see the bigger impact from a bottom line perspective.